All right, so in the lab what happened is we got our ticker tape. This is what it looks like. You can see this is where the first dot, where the trigger was being held. So what we're going to do is this first non-trigger dot, I'm going to put a line here, and then I'm going to label this 0. So this is my time equals 0. And then I'm going to go through and I'm going to draw straight lines on every single dot. Okay. Now as I go through and I do this, then I'm going to go back after I draw those lines and I'll label this 1, 2, 3, 4. Okay. Now if you remember, each dot is a 60th of a second apart. So this is 0 seconds. This is really 1/60th of a second. This is 2/60ths of a second, 3/60ths of a second. And then what you're going to do is to the nearest hundredths place, you're going to get this out and you're going to measure between the two dots. So when I look at this, right, I had that's 0.5, 0.6 and a half. So this is 0.65 centimeters. So you're going to use the centimeter side and you're going to go through and you're going to measure between each line. So on here, I have 0, and between 0 and 1/60th of a second, this was my displacement, 0.65. And then to get the next one, between 1 and 2, so I go between 1 and 2, and then I measure it out, and I get that it's 1 centimeter apart. Now, if you'll notice up here, I already labeled my graph. So I have displacement. I'm showing that I'm measuring it in centimeters, so you'll want to include that. So this is how we get the displacement graph from the ticker tape. Okay? So you're going to go through, you're going to do all that, you're going to fill in as much of the table. Now notice at the end, I have 9.8, and then the next one that I measured at the end of the tape was 9.1. At this point, I know that the ball must have bounced, and it started to come back up, so I just eliminated that set of data, all right, immediately. Now, there are some places, like these are really close, 4.7, 4.75. I feel like there was one that was identical, maybe not. So the only thing, like sometimes like you will get numbers that are close, because remember, as the ball is falling, that ticker tape is also moving around, so there are sources for error in that. All right, so then, so the displacement is just the measure between each mark starting at t equals 0. Now we want to get the position. Now the position, you're going to start with 0 and you're going to add each consecutive displacement. So right now, this is my 0 position. So if I have this displacement, right, if I want the position at 2, I just need to add both of these together. So this is where your calculator will come in handy. So what you're doing is you're going to put 0 plus 0.65 is 0.65. Now I have this 0.65, and then I have 1. So 0.65 plus 1 is 1.665. 1.65 plus 1.2 is 2.85. And then what you're going to do then is just go through the whole thing. So it's just adding the next number. So do you guys see how it's kind of diagonal here? So 9.8 plus this is 12.5 plus this is 15.35. So you're just going to go back and forth, okay? So that's how you get the position. And then to get the average velocity, what we're going to do is we're going to get the average velocity for every 1/60th of a second. So what I'm going to do is I'm going to take my displacement during that 1/60th of a second. Now, if you're dividing change in position over time, right? So the displacement divided by the time, that's the same thing as multiplying by 60. So delta x divided by a 60th is the same as 60 times delta x. So for the average velocity, what you're going to do is here we have 1/60th of a second. My displacement was 0.65. 0.65 times 60 is 39. Times 60. 60 times 1 is 60. 1.2 times 60 is 72. So you're literally just going to multiply all these numbers, and you see how they line up. And I would suggest, even if you want, just take your straight edge and move down. So 1.5 times 60 is 90. 1.6 times 60 is 96. And you're going to fill in the average velocity. Now again, this is the average velocity during that time frame. Okay, so just for that 60th of a second, that was the average velocity. Then we need to get the average acceleration. Average acceleration is the change in velocity over time. Well, we're going to do the change in average velocities over that 1/60th of a second. So again, instead of dividing by this fraction, I'm going to multiply by 60. So I have my v minus v naught divided by 60, all right? So the delta v's I'm looking at over here, here's my final velocity, 60, right, minus 39, and the change in time here was a 60th of a second. So 60 minus 39 times 60 is 1260. So this one takes a little bit longer, and you're going to be using 2 at a time. So notice the 1260 is in between these two, so that you find the difference and then multiply by 60. So I move down, 72 minus 60 is 12 times 60, 72. Move it down, 90 minus 72 times 60. 96 minus 90 times 60. And you're going to go through. That's how you're going to fill in the acceleration table. Now, once you're done with this, okay, hopefully you guys will all get the table done today. That is the goal, all right? And then for homework, you guys are going to have to draw this. So you have your position versus time. If you're doing it right because it's accelerating, you should get a nice curve. Now, I did not draw in the line of best fit. You guys do need to do that. So you're going to actually draw the curve. So in here, it doesn't make sense to draw a straight line because the straight line is not a good fit for this graph. So this data, it would be a curved line of best fit. It's a quadratic fit, all right? For the velocity versus time, so this is what my velocity versus time looks like. Again, you would draw a straight line of best fit. Now, in analyzing the data part of your lab, you are going to get the slope of this line, okay? The other thing you need to pay attention to for velocity versus time is notice the velocity, it's in these middle points. Oh, let's take a step back here, sorry. Position, we're measuring, or we're graphing position versus time, not displacement versus time. So that is the purpose of getting this table. So these were all the positions, so do be careful for that. So position versus time. The other thing too, I made time 1/60th of a second. That way I could just do 10, 20, 30 instead of 10 over 60, 20 over 60, 30 over 60. Does that make sense? Right? So this isn't really 10. So when I'm finding, like when I'm down here and I'm finding my slope, this isn't 30. This is really 30/60. So this is really a half a second right here. Okay? All right. All right. So for the velocity versus time, going back, notice the velocity, right? It is in between, right? So this first velocity you have, that 39, that was the average velocity between 0 and 1/60th of a second, okay? That was the average velocity of that time. So I just did a shift. So here, this is really at 0.5, 1.5, did I say that right? Yes, 1.5, because this is 2, so this is 2.5, 3.5. So everything's on the halves. Okay, so here if you look, this is a 2, right? So 1 is in the middle, and notice these are on kind of the quarter markings. So that is your velocity versus time graph. Your acceleration versus time, what I want to point out, I did 2 of them so you kind of can see. Generally, we are trying to use as much of the graph as possible. But if I draw the acceleration versus time graph, what do we know about what the graph should look like? It should be a straight horizontal line, right? So I'm supposed to figure that out from this. But if I use as much of the graph as possible, it's kind of like, whoa, like I have no idea where to draw that. Notice, though, if you change the y-axis, right, so that our data points are closer together, you do see that it's going to be a horizontal line in comparison. So it does help to change your scale to make it look more horizontal. However, still, this is not necessarily the best way. So what we're going to be doing is we are going to use the slope from the velocity versus time graph. So once you draw your line of best fit and you get the slope of that, you're going to come over here, and whatever number that is, you can draw your straight line, and you can kind of see where it falls in your data set.